This question is a linear programming question. It says a gold processor has two sources of gold ore, source A and source B. In order to keep his plant running, at least 3 tons of ore must be processed each day. Ore from source A costs $20 per ton to process, and ore from source B costs $10 per ton to process. Costs must be kept to less than $80 per day. Moreover, federal regulations require that the amount of ore from source B cannot exceed twice the amount of ore from source A. If ore from source A yields 2 ounces of gold per ton, and ore from source B yields 3 ounces of gold per ton, how many tons of ore from both sources must be processed each day to maximize the amount of gold extracted, subject to the above constraints? Okay, so we've got two locations that we're taking ore from. Both locations, it's known data that I'm going to get more ore or more gold per ton of um, material from one source than I did from the other, but it might cost more to use that source. And then I've got regulations that says you got to use so much from this source, you got to use so much from this source. So how can I learn as a businessman what I need to do and to maximize my overall profits eventually? How can I get the most gold out of the ground by following the constraints that we've learned here? First thing you want to do is talk about your objective function. Okay, and remember the objective function is basically the overall goal of uh, the scenario. Okay, and if we look at this, it says how many tons of ore from both sources must be processed each day to maximize the amount of gold extracted. So I want to maximize the amount of gold extracted. Okay, so the max extracted gold is going to be equal to, it's going to be, I get 2 ounces from source A and I get 2 ounces, or sorry, 3 ounces from source B. Okay, so if we were to let source A equal X and source B equal Y, um, the maximum extracted gold is going to be 2 ounces from A, so 2X, and 3 ounces from source B. And again, this is per ton, so however many tons I get from source X, or sorry, source A times 2, and however many tons I pull from uh, source B, which is our Y value. Okay, so that's the maximum extracted gold, 2X plus 3Y. Right? Now, working our way through this question, we have many other constraints. Okay, it says in order to keep the plant running, it says at least 3 tons of ore must be processed each day. Okay, what that means is, I could process 3 tons from source A. I could process 3 tons from source B, and then obviously it would be none from the other source. Um, or I go 1.5 source or tons from each source, or I go 1 from source A and 2 from source B, or so on. Okay, so we're gonna have some constraints here. Um, the first which being the process constraint. Okay, and I'm gonna do that in blue. Says at least 3 tons of ore must be processed. So from source A and from source B, I have to have at least 3. Now, at least, that keyword means greater than or equal to. All right, so we get that constraint, and that's a process constraint. I just like to label um, each constraint um, so I can maybe later go back and know what was x y plus or x plus y greater than or equal to 3. What did that refer to? It says ore from source A costs $20 per ton to process. Ore from source B costs $10 per ton to process. Costs must be kept to less than $8 per day. So here is an additional constraint. It's called a cost constraint. Okay, um, or some people refer to it as a resource constraint. $20 from source A per ton. and $10 per ton from source B, and I have to keep that to under 80 bucks. And I'm just going to make it the way I've worded this question. I probably should have said no more than $80 per day. So because of the equality, when we do these, we're not going to really be too concerned with dotted lines and solid lines. So let's just assume they're all less than or equal to, greater than or equal to. Okay, and that was a cost constraint. Going through it, it says federal regulations require that the amount of ore from source B cannot exceed twice the amount of ore from source A. A lot of times working in mining and stuff like that, there's many regulations. There's water regulations, there's mineral regulations, there are all kinds of stuff, or digging regulations. Then you just gotta follow them. So in this instance, they've got a regulation where you can't work as much in one source or one location as you can in another. It says the ore from source B cannot exceed twice the amount of ore from source A. So B, which is our Y value, I'll do this in green, our Y value has to be less than, it cannot exceed, so less than or equal to, twice the amount of what we get from source A, so 2x. And this is our federal regulation. Right. And now the things that we usually don't graph are the non-negative constraints, which are just going to say, you know, x has to be greater than or equal to 0, and y has to be greater than or equal to 0. And what that does is say, well, then I can't dig up -3 tons of source A and -15 tons of source Y to maximize my profit. It just doesn't make sense. Also, the non-negative constraints, you know, if I were to graph them, it's going to be the positive side of the x-axis, the positive side of the y-axis, and then it just creates, you know, this feasible region over here, which would be the first quadrant, ultimately giving us back always positive values, or 0, because it could be non-negative, for our corner points. Okay, so I'm going to go ahead and graph these inequalities and see if we can learn anything about this question once we do that. That first inequality is x plus y is greater than or equal to 3. I'm going to use the idea of x-intercepts and y-intercepts to graph this. You know, if I know x is 0, in this case, if x is 0, y is going to be 3. So you got 0, 3 as one of my points. And I'm going to go ahead and just label it 0, 3. And later on, you're probably going to see why it's a good idea to label these things. You know, for the same reason, if y was 0, x would be 3. So at this point here of 3, 0, we'll go ahead and connect those. Not what I wanted. There we go. Okay. And now, because it was greater than or equal to, we would want to shade everything above that line. So that's, you know, right now with just one inequality drawn, we've got this feasible region of infinite solutions up here, which, you know, adding the other constraints is going to limit that region. Doing the cost constraint, you know, if x was 0, y is going to have to be 8. So x is 0, 1, 2, 3, 4, 5, 6, 7. Let's just put 8 right there. So 0, 8. X is 0, y is 8. When y is 0, x is going to be 4. So 1, 2, 3, 4. Alright, and then I'll connect those. Okay. Now, you know, we had to shade less than or equal to that line. So, you know, it'd be everything down here All right, but we're looking for where that line, the inequality for that line and the inequality for the blue line overlap each other, and they're going to overlap each other in that yellow region there. Okay, so right now that's my feasible region. I now want to look at y is equal to 2x. Okay, so again, we can graph this, a y-intercept of 0, 0, um, and then slope is up 2 over 1, so slope's going to be about right there. Probably do this in green. Connect those. Excuse me. Green. And now it says, I got to shade less than that. So now less than this green line would be all this stuff, but we want to make sure that's overlapping with the other inequalities. So eventually when I've graphed everything, shaded everything correctly, I should get this region here. Okay. And that yellow region is my feasible region. Now we had talked about in class how the corner points of our feasible region are the points that are going to provide us with a potential, or those are the potential points that are going to provide us with an optimal solution. Okay, so really those are the only points that I'm concerned about in this region. In order to find those, we've got to use, essentially systems of equations to determine what that ordered pair is. What I'm going to do is I'm going to take, if I look at this blue line and this green line, okay, so the blue line was x plus y. I'm going to just say is equal to 3, and y is equal to 2x was the green line. With this, I could use just basic substitution to go ahead and find out what x and y are. So, if y is equal to 2x, I'll just go ahead and say x plus 2x. Just taking that y and replace that y right there and replace it with 2x. And I get 3. So I get 3x is equal to 3. So x is 1. And then when I plug that in here, I'll get y to be 2. Oh, yeah, I just say y is equal to 2. Okay. So this point right here, 1, comma, 2. And now I'll do the same thing for the red line and the green line. The red line was 20x plus 10y is equal to 8. Or sorry, 80. And the green line is y equal to 2x. Again, I'm just going to go ahead and use direct substitution, change that y to 2x. So I got 20x plus what ends up being 20x again, when I substitute, is equal to 80. So 40x is equal to 80. X is equal to 2. I'm going to plug that in. Y is going to be 4. So that point right there is 2, 4. And now do the same thing down here. And I really don't need to do the same thing down here because I already know at that point right there is 3, 0. And that point right there is 4, 0. So those are my potential solutions. One of those is going to yield me an optimal value. Okay. And what I've found useful in the past is for people to create just a quick chart like this with a vertex in this column and the objective function of 2x plus 3y in this column. And remember, that's going to be a maximum. The vertex of 1, 2. I've got the vertex of 2, 4, and then 3, 0, and 4, 0. Okay. And now I'm just going to plug those values in here. 2 times 1 plus 3 times 2 is going to give me 2 plus 6 is 8. So 8 ounces of gold right there. Okay. If I try 2, 4, so 2 times 2 plus 3 times 4. 2 times 2 is 4 plus 12 is 16 ounces of gold. And if I try 3, 0, so 2 times 3 plus 3 times 0 gives me 6 ounces of gold. And then 4 comma 0 is 2 times 4 plus 3 times 0 is equal to 8 ounces of gold. So looking at these, that value right there is a maximum. So 16 ounces is going to be my optimal solution. So what that means is the point 2 comma 4, that vertex says I need to dig 2 tons from source A and 4 tons from source B to extract the maximum amount of gold.